The goal is that this is a contradiction. So let's just try to mess around with both sides. And as a reminder, we have Archimedes' property to work with. Should I put Archimedes' property on the board also? What does it say?
Natural numbers are not bounded above.
So there's a thing we know, and this is like what we're using. Let's try to contradict that. Let's try to mess around with this and see what we can get. What seems useful to do? Yeah.
Looking ahead in the proof, we can multiply both sides by the inverse.
Mm-hmm. Also known as dividing by a, I guess, if you want to say it that way. What happens when you multiply both sides by a inverse?
N is less than or equal to b times a inverse.
And let's see. That only happens if we multiply both sides by a positive. Is a assumed to be positive? Cool. I claim that that's a contradiction. And maybe pointing at this, tell me why is it? That thing. Yeah, right. That thing is this thing. Yeah, cool. That seems like a proof then, right? Let's just add those ones. Doing that thing, multiplying by a inverse, we see that from every natural number n is less than or equal to b times a inverse. Do you think it's important that I said multiplying by a inverse instead of dividing by a? At this point, no. Those mean literally the same thing. Oh, we did. We did. That, like, right after the field axioms, I say that by a divide by b, we mean a times b inverse.
Okay, so we can talk about division in our proofs then.
Yeah. At this point, yeah. If you said it in like the field axioms proof, then I would say, well, I'd rather you say multiply by a inverse because then you really see where commutativity comes into play. But at this point, like anything you can do with division and inequalities, you can now do it. Okay, nice. So what thing do we now know is an upper bound on the set of natural numbers? Nice. But we know that there isn't an upper bound on the natural numbers by the Archimedean property, so there's our contradiction. Where we go? Oh, what? It's on the table then. Groovy. So, here's one that I will have you do in fact for homework. Here's a claim. The infimum of the set containing reciprocals of natural numbers is 0. And maybe let's just get a sketch going off to the side. What do you need to do to prove something is the infimum? What's the definition of the infimum? It's the highest lower bound. And that means there are like two things you need to show. You need to show that it's a lower bound. Does it look reasonably obvious to show that 0 is a lower bound on this set? Yeah. Right, you would consider any element of this set and use the fact that natural numbers are positive to show that 1 over a natural number is positive. Maybe you could even like cite a homework problem that you've proven that 1 over a positive is positive. Next, you need to show that 0 is the greatest of all lower bounds. Does that again look like something? Well, that might take a little bit more work. But mess around with a few things. Maybe use the reformulation in terms of an arbitrary positive number. There's a homework problem that'll guide you through this one. So, with that in mind, let's keep on plugging along. My eventual goal in this packet is, well, I'll flash over to the theorem. The density of the rational numbers. For any real numbers, x and y, with x being less than y, there is a rational number q which lies between them. And again, is that something that is like internally obvious? Like if you picture these things on a number line, yeah, there should be a rational number between any two reals. But saying it's obvious is not a proof. Saying it's obvious means that you don't really know a proof, and this is something that you believe is true somehow. We will prove it probably reasonably soon. On the way, we will prove the following. Claim for any z in R, there is an integer somewhere between z and z plus 1. Again, like that's something that seems intuitively true. Let's try to prove it. And maybe we'll even try to sketch a proof. Oh, there's an outline. So let's read the outline. As we read, I'll put things on the board. So, for any fixed real number z, we need to find a natural number n. An integer, so that n lies between z and z plus 1. So maybe we'll just try to write that out as a proof. And we start by just being assigned a real number z. Let's maybe split this into two different things. If I asked, can you find a natural number n that's bigger than this fixed, an integer n that's bigger than this fixed real number z, could you? Yeah, why? Yeah, there's no upper bound, I guess, on the integers is what I care about. Because this n is supposed to be in the integers.
You say that natural numbers in all the bottom are supposed to be natural bigger than z.
That's true. Like this, at this step, this could be true for just the natural numbers. The reason I want it to be the integers is because I also need this to happen. And let's maybe draw a picture. There's z plus 1. If z were like negative 9,000, could I find a natural number between those? No, so there's an issue with negatives. I really do mean integers. So let's picture what we have so far. This says that there is some n that's bigger than z. Maybe it's over there. Well, it's annoying, right? That n it might be bigger than z plus 1. That would make me sad. But like there should be an n that's bigger than, that's in between those two, right? So like maybe instead of trying to pick like any n here, I can try to take like the least of all of those n's. That sounds a lot like maybe I'm taking an infimum of a set, right? So let's consider all the natural numbers satisfying, I'm doing this in the wrong order, n less than or equal to z plus 1. That set should be non-empty because the integers don't have a lower bound. I guess here I'm using that the integers don't have an upper bound. Oh, but now that's a set that's non-empty and bounded above or below, depending on which strategy you're following. So it has a supremum slash infimum. Maybe I can prove something about that. So there's like the strategy I want to follow. Let's try to put it into practice. Cool. All right, so let's do it. Let's let A be the set of all integers, satisfying that that integer is less than z plus 1. I want to explain why this A is non-empty, and I think we can do it in like one sentence. So tell me, why should that thing not be empty? Let's try to parse out what we're trying to show. So this is like scratch walk off to the side. So we want this set, the set of all n, such that n is in Z, such that n is less than or equal to Z plus 1, not empty. So that means I need something to be in that set. What would it mean? What does it mean to be in that set? So we want that there exists something in Z with that thing less than or equal to Z plus 1. Fair enough? Why should there be an integer that is less than or equal to Z plus 1? Let's see, is Z plus 1 an upper bound on the integers? Why not? They don't have an upper bound. So let's start with this. Z, math beat easy, the integers, have no upper bound. And I guess if we want to be precise, we have proven that it is corollary 2.6.4. So Z plus 1 is not a lower bound on Z. All right. Well, it's not a lower bound on Z, so what does that mean? What does it mean to not be a lower bound?
There's something else that is lower than that?
Yeah. There's something in the set that's lower than it? So, there is some n in the integers with n less than Z plus 1. Does it follow that that thing is in the set big A? Yeah. Is n an integer? Is it less than or equal to Z plus 1? Yeah, it's even strictly less than, but that's okay. Since n is in A is not empty. Cool. Now, tell me, why is Z plus 1 up or down on the set big A? Find the name. Yeah, it just follows from the definition of it. But let's try to be very formal. How should I prove that something is an upper bound be formatted?
For all n in A, n is less than or equal to Z plus 1.
So we need to let n be in the set big A, and then we need to conclude that n is less than or equal to Z plus 1. So how do you go between the start of that line and the end of it? Well, like you said, it's just the definition of the set, right? It's in this set. So set builder notation means by the definition of A, then n is less than or equal to Z plus 1. Oh, is that just like everything? Yeah, so like it's super obvious, but you do need to format it as a proof that something is an upper bound. Okay, we feeling good? the set A that was just defined is non-empty and bounded above. What's true about sets that are non-empty and bounded above? Yeah. The real numbers are complete, which means that, yeah, they have a supremum. So completeness says that every set that's non-empty and bounded above has a supremum. So by completeness of R, A has a supremum. Let's call it S. Feel pretty good? Nice. So here's the strategy we'll use. So I'm going to try to use something about the supremum to come up with this choice of n that's between these two things. So here's this thing S. I don't already know that S is an integer. Right? It's a real number. The integers, we don't have any completeness about them. But maybe we can say something about how it interacts with z plus 1 and z minus 1, and maybe we can come up with some n using some tricks there. Does that seem like a not totally insane plan? I hope so. Let's see what we can do. S is the supremum. So S minus 1 is less than S, right? So what can you conclude about S minus 1 since S is the supremum? It is not an upper bound. And I know that A is the only set in question, but maybe I'll specify it is not an upper bound on A. Since it is not an upper bound on A, what can you conclude?
There exists an n in A such that n is greater than S minus 1.
Nice. S minus 1 is not an upper bound, so there has to be something in the set bigger than it. People comfortable with that jump? Excellent. There exists some n in A, so that n is bigger than S minus 1. Okay. Well, plugging along, we're doing okay. All right. This n, it's in A, right? Right, it is. So n has to satisfy the defining property of A. So since n is in A, what can we conclude about n? What does it mean to be in that set?
N is less than or equal to C plus 1.
Cool. And that's good. That's like one of the things we need. So I guess getting something less than or equal to z plus 1 wasn't so exciting. But it seems like this is like one of the biggest things that are in the set. So let's see what else we can do with that. So let's see, right now we have n is bigger than s minus 1, right? So what can you tell me about s as compared to n plus 1? It is less than this. Add 1 to both sides of that. Wait, so n plus 1, could that possibly be in the set big A? Nope, but it is an integer. So that means this thing can't be true. So, n plus 1 is not in A. So n plus 1 must be bigger than z plus 1. And remember, we still have this goal floating around. We need n to be bigger than z. Oh, do we now have n is bigger than z? Yeah, n plus 1 is bigger than z plus 1, and so what can we conclude since n plus 1 is bigger than z plus 1? Exactly what we want. N is bigger than z. Oh, cool. Have we now found a single integer which, let's just see if we have everything we need. Do I now know that n is strictly less than z? Do I also have, come on, Chris. No, I don't. I don't have that. Don't just blindly agree with me. What do I have is less than the other thing? And let's just go back to the original statement of the theorem, because a lot of stuff happened. Let's see if we actually achieved what we wanted. There's like a Helmholtz box there at the end, so this better be the end of the proof. Oh, in fact, I think I see something missing. Did I start this proof by making it clear that I'm considering an arbitrary z in the real numbers? In fact, did I declare z at all? Maybe we better just start this with a quick consider any z in R. Does everything that I did walk for an arbitrary choice of z? I think so. Right? As soon as you say that, like, you now have a fixed z in mind. Now I'll declare A. It's non-empty. It's bounded above, so it has a supremum. You can do supremum minus 1 and come up with an element of the set. Yeah, I think it all works. And eventually I get z less than n less than or equal to z plus 1. Is that exactly what it means to be in this interval? Cool. And I think that proof's complete. All right. So, finally, the proof that the rationals are dense in the reals. Let's try to prove that. So let's start with kind of a number line based picture of the proof. So again, we have x less than y. We want some rational number q equal to n over m that sits between those two. The n and m might not line up. M over n. Let's make it m over n. That'll agree with the proof. We want an m over n between these two things. Well, but right now, like, it's unfortunate that we're looking for like a rational number. Let's just try to simplify. I'm going to start by like multiplying both sides by n. It's a rational number, so I may as well assume that little n is a natural number. So I really want n less than nx, less than m, less than ny. And I just need to come up with a choice of m between those two things. And in fact, I get to choose n also. So I can make n really, really, really big and m really, really, really big. And one thing I can definitely always do, I can always get nx less than m less than or equal to nx plus 1. Right, that's the theorem that we just proved. You can find an integer between nx and nx plus 1. Do you think I could eventually get nx plus 1 to be less than ny by taking n to be big enough? If x is less than y? if we could, we'd like be really happy, right? Because then I could like go backwards through these steps. So. So let's see what that would mean. Let's try to get all of the n's on the same side. Those two things are the same? Ooh, wait, so this should be like promising. This says that if I multiply y minus x by something big enough, I can get that to be bigger than 1. Do I have a theorem that says we can do that? Cool, okay, nice. So this has all been like a sketch. And like most of the work in coming up with this proof would have been before you put any pencil to paper on. Well, before you started writing your final draft, doing a bunch of stuff like this. Eventually you can, so let's start here. Oh wait, so let's actually look back at that theorem that says if we can multiply a thing by a big enough integer to get it to be bigger than 1. There's an assumption on the thing that you're multiplying by an integer, by a natural number. What is the assumption? Not 0, and a little bit stronger than that. Needs to be greater than 0. Do we have that y minus x is bigger than 0 right now? Yeah, well, we don't like literally have it, but we do have it, right? Why is y minus x bigger than 0? Y is bigger than x. So I think, hopefully, this is the right place to start. So let's let x and y be inner. Assume that y is bigger than x. So y minus x is bigger than 0. And now, let's crank through these steps in reverse. This will be the whole spirit of the proof. And the reason that I did that sketch is because otherwise this proof would not be followable. So a lot of times when you're trying to come up with a proof, you like start with the thing you want and manipulate it. But no formal proof is actually that. Right? Like maybe when you took pre-calc, you did these like 2-column proofs where you started with an equation and simplified it. But really the logic in doing that is like wrong. You're assuming what you wanted to show and then trying to reduce that to a truism. Really all of those pre-calc proofs are upside down. At the bottom you have something you know is true and then you complicate it to the thing you want. Anyway, that's not the point. I'm getting distracted. All right, so let's go for it. So let's appeal to theorem 2.6.5 with a equal to y minus x and b equal to 1. Let's just see if that's the right thing to appeal to. That theorem, 2.6.5, says that for any real numbers with a bigger than 0, we have that. There's a natural number so that a times n is bigger than b. So let's use that. So there is some natural number n satisfying that. What do I get? I mean, you can say it maybe with a's and b's first, and then we'll write it down correctly.
A times n is greater than b.
Cool. And now let's put the actual what a is and what b is in. So this becomes
Y minus x times n is greater than 1.
those parentheses matter, but I don't think I need to emphasize that for you. So now I'll keep cranking backwards. So it follows then, I guess take this and isolate ny. What does it become?
Y is greater than 1 plus n.
Excellent. Excellent. So the next thing that was like something we wanted to do was, so ny is now bigger than 1 plus mx. That's the same as what's written on the ball because of commutativity. Next thing we did is we exhibited an integer between these two things. So let's use the theorem that tells us we can do that. Let's appeal to lemma 2.6.7 with z equal to nx to conclude that there is some m in z flashback to 2.6.7. What does 2.6.7 do? What's the conclusion of this of lemma 2.6.7?
nx is less than m, less than or equal to nx plus 1.
Cool. Okay, and you've already plugged in what the variable names are. Excellent. So let's write down that conclusion as 2.6.7 is like z is less than natural number is less than or equal to z plus 1. But it doesn't matter that this is called n, and in fact it shouldn't be because n already has a job. Let's call it m, and z was nx. To conclude, there is some integer m with nx less than m less than or equal to nx plus 1. All right, we trucking along? So let's see. This is the step above, so let's just try to explain why this is true now. So right now, we have nx less than m, and we know that m is less than or equal to nx plus 1. Okay, cool. Nx is less than m, that's a start. I need this thing to be less than ny.
Nx plus 1 is less than ny.
Nx plus 1 is less than ny. And you know what? One thing that's often useful is having labeled equations by triangle, nope, star first, and triangle. And in this document, they're all labeled with numbers, so I don't want to use a number because the numbers will already have a job. Oh, neato. So I now have nx less than m less than ny. How do you go from there to the thing we want? By y. Or by n, yeah. Divide everything by n. And let's maybe do a quick sanity check. The n we produced, I'm claiming here that it's a natural number, and so it's positive. N showed up as a consequence of 2.6.5. The thing produced by 2.6.5, I sure hope is actually a natural number. Is it? Excellent. Okay, cool. So we can divide everything inside by n, or multiply everything inside by n inverse, tomato, potato. No, in this case, tomato, tomato is appropriate. They are the same. To get x less than m over n less than y. And the concluding sentence is we have just produced the needed irrational number, and there were a lot of bits to this. So I think it's worth walking through this proof and seeing if it actually does the job that I claimed it did. So we needed to show that for any real numbers x and y, assuming that x is less than y, there is a rational number q which lies between x and y. Okay, so I considered any real numbers x and y. I assume that x is less than y. I concluded that x is less than m over n is less than y. Does that actually accomplish what I needed? And it was like a single choice of m and n that I produced, which is all I needed. I just needed one choice of m and one choice of n. Yeah, so this proves that theorem. I feel like there's one thing lacking from this exposition. Have I actually stated what the definition of Q is? Do you know what the definition of Q is? What is the definition of Q?
N over M such that M and N are integers.
Oh, yeah.
And the denominator is not zero.
Yeah. And depending on like how you feel, maybe you would say, well, you don't need to include that because if it is zero, then this isn't a thing anyway. But it's worth having that little check. In fact, if instead you had n is a natural number instead, would that be the same definition? If you had any rational number, you could arrange that the denominator was positive. Makes me feel silly that it's not. That definition.
Well, it needs to be negative because both the numerator and the denominator are natural numbers, so you can't get any negative rationals.
Only m is assumed to be in the naturals. Yeah. So you would just, the numerator can be negative, the denominator can't. Groovy. So some of these proofs had like a lot of parts. They weren't necessarily things that I would expect you to come up with during the course of like the 50 minutes that I gave myself. So like there's always two levels of understanding an argument. Do you follow how like, was it clear how each step followed from the preceding steps? Did that bit make sense today? Good. The like deeper level of understanding a proof is convincing yourself that you could come up with it starting at the beginning. And take a look at these proofs, and I tried to give some motivation, so hopefully that helped some. But these proofs are actually just like kind of complicated, right? So look back through them and see if you could come up with some of those ideas. And I've given you, in the form of homework, some things to think about. The first is to imitate the proof of the density of the rationals to prove the density of the irrationals. Where, I mean, I guess again, like, I don't know, there's a definition of irrational. A real number is irrational if it is not rational. Prove the density of the irrationals, and then prove this corollary 2.6.6, and try to follow the ideas that we built up in this document so far as you do that. And while you do that, you'll need to think about definition of supremum and infimum. Nice. So I do have a little bit more to hand out, so maybe I will. Next time we're going to start in on new content, which I guess makes sense because the only thing left in this is a single challenge problem in which you'll prove that square roots exist. So what I'm handing out right now is the first two sections of chapter 13. Only the first two sections because I wanted to make some revisions in this as I made some. So I'll hand out the rest of the chapter on Wednesday as we start going through. Did I hand someone too many copies? Ah. Okay. Thank you. Cool. So I feel like I'm at a good stopping place here. The maybe definition question I was going to ask is what's the definition of the limit of a sequence? And in fact, maybe I'll encourage you all to do this. I haven't made any explicit references to the Coughlin textbook that this class is associated with, right? The screen textbook that you got from the bookstore. I think I'm going to ask you in the form of a pop quiz on Wednesday. What does it mean to say that a sequence converges to a number? So the thing in there that's not filled in, definition 3.1.2. I'm going to ask you that as a pop quiz. It'll be slightly unfair because I haven't told you what it is. But you know what the limit of a sequence is. Right? If you took calc 1 and 2, probably 3 also. Nice. All right. Then I'll stop there. And I definitely don't want you to like panic about looking up that definition. I think Wednesday's lecture will be nicer if you do. Ooh, anyone planning on coming to my office hour? Okay, cool. Oh, wait, as people are packing up, how many people in this class are currently looking to meet up with other people in this class and find a time to work on the homework with this class with each other? Okay. Okay, both of you shook your hands, so like look at each other and maybe try to find a time.
I'm just asking this because I'm curious. So we know that there's always irrationals between any two real numbers. Is there a way to, based on any arbitrary real numbers, figure out a concrete rational list between them?
Oh, sure. Like, can you make this proof constructive or something?
Yeah. I don't think this proof is helpful for that. I mean, we know that it's true.
So some existential proofs are really hard to turn into proofs that give examples. Mm-hmm. But I think this one could, in that. So like, what did? Like, I think it would be tracking through all of the steps that are performed. Step one is to do this with that. So you want to come up with a concrete choice of making that happen. And so maybe I'll make it this 2.6. So step one would be trying to adapt this proof to make it one with here's an example.
Right.
And so what was the proof here? It was like, oh, come up with there's something bigger than b times a. So I think it would be reasonable to come up with an example starting with the following. An operation called the ceiling function. Oh, W has to W. This is solid. Like 80%. So I think if every time you need to find a natural number less than or equal to some number, if you define this floor function, and I guess you need to check that this set's not going to encounter it. It is.
Okay.
So I think if you do the following, check that these two are actually functions. Check that they're both actually integers. Then I think you can take all of the proofs in this packet and say, this is the example you're looking for. And then eventually, what? What? Yeah, I think that would be a way to do it.
Okay, I might do that in my own.
Yeah, and there's somewhere in the overlap between analysis and algebra, there's the idea of what's called well-approximable real numbers, which the idea is for any real number, you can find rational numbers close to them. And if you give yourself a particular epsilon neighborhood, there's some like P over Q over this. How big does that denominator need to be? As epsilon changes.
Wait, what are we saying P is here? Just a number?
An integer. I guess Q is a natural number. Okay, cool. So you have some x to start with.
Okay.
Then for any epsilon, you can find a P over Q in this interval.
Oh, in the interval. Okay.
And what's the smallest Q that can do that?
Okay.
As epsilon gets smaller, that Q has to get bigger. Depending on how that Q grows with epsilon, you call that real number x well approximable by rationals.
Okay. So we're just trying to get close to irrationals using rationals.
Yeah, but using irrationals that are like as rational as possible.
Okay.
With that Q not being too big. It's also got the like algebraic properties of real numbers are kind of detected by that. Like if you have something that is the root of a polynomial, so an algebraic number, then it is not well approximable. So one way to check if something is the solution to an algebraic polynomial is to try to approximate that.
Do any chance have a review?
Yeah.
Because
Yeah. They're reasonably written things you can